Present day, everyone. Welcome once again to our session for today. So we are going to focus our discussion today on discontinuity. So this is just related to what we had discussed on the topic about continuity. Alright, so we have here discontinuity. This is a point at which the graph of a relation or function is not connected. So discontinuities can be classified as either removable or essential. So last time we talked about removable and essential discontinuities, but we have no details yet on this essential. Alright, so we are going to discuss more about this essential discontinuities in this session. So there are several kinds of essential discontinuities, one of which is the steep discontinuity. So like in this graph here, it's an example of steep discontinuity. Okay, so for example, the right hand limit, so as you trace the curve here, it stopped here, and it's step up. So as you move, for example, as x approaches to a certain value here, so when you're tracing this curve from the right, going to that value approaches by x, so it goes like this, and then when it reaches here, okay, it step up here, and then continue until where that value of x is being approached by tracing this curve. Okay, so this is an example of a step up discontinuity graph, and we have here what we call removable discontinuity. Okay, so for more details about this, you can check this one from this source below. Okay, so when we speak of removable discontinuity, or we call it a hole, so a hole in a graph, that is what we call removable discontinuity. So that is a discontinuity that can be repaired. So how to repair that discontinuity? So we can do it by filling in a single point. In other words, a removable discontinuity is a point at which a graph is not connected but can be made connected by filling in a single point. Okay, so formally, a removable discontinuity is one at which the limit of the function exists but does not equal to the value of the function at that point. This may be because the function does not exist at that point. So, an illustration of this removable discontinuity. So, you can see it here. So, as you trace the graph from the left going to the right, okay, so there's a hole here. So, this makes the function or graph discontinuous at this point, and then it continues here as you move, continue tracing the curve. Okay, so this can be removed by just filling it or filling in a single point. Okay, so filling this point here with a single point. All right, so that's removable discontinuity. So next we have step discontinuity, or we call it jump discontinuity. So a discontinuity for which the graph steps or jumps from one connected piece of the graph to another. So formally, it is a discontinuity for which the limits from the left and right both exist, but they are not equal to each other. Like for example, if you trace the graph, no, so if you find the left hand limit, so as you trace the graph from the left, okay, so this is the limit, a certain value, this limit, and then if you trace it, this graph from the right, so we take the right hand limit, so trace the graph going to this point here as it approaches to a certain value here. So you see, this is the limit. Now if you compare this limit and this limit, they are not equal to each other. Okay, so that makes this a discontinuous function. So this is the example or an example of step or jump discontinuity. Okay, once again, the details could be found from this link below. So we have what we call the point discontinuity. So oftentimes we encounter point discontinuity when we get the indeterminate form and we are able to use the cancellation technique, right? For example, here, if you're given, so original, this is, I think this is x squared. I think the original equation here is, that is coming from x squared minus 3x plus, or sorry, this is minus 6, right? Then divided by, sorry for that. So originally the limit of this function, this is a rational function. Okay, and then we just use the factoring here to factor this one. These are the factors, so you can, if you see the numerator, we have terms or something in the numerator which is similar at the denominator. Okay, so we can divide it, and we got it so when you divide this factor with the same factor at the denominator, okay, so this, you have x plus 1. All right, so this is what is meant by this point discontinuity. So point discontinuities are considered to be removable. Okay, so if you graph this function, so it will show you this kind of graph. So at this point, the function is discontinuous, and this can be repaired by just filling in this single point here. Okay, so by just using this, like this is x minus 3 divided by x minus 3, so what is left here, so this becomes, limit of x, so what is left is limit of x plus 2, right, as x approaches to 3. Okay, so by doing this, alright, so what is the limit? The limit here is equal to, so substituting x equal to 3 to this x in the denominator, this, because denominators, numerators already equal to 1 when you divide them. So what is left is x plus 2. So when you substitute x equal to 3 to this function, so you have 3 plus 2, that is equal to 5. So we're now able to fill in this point of discontinuity with this single point. Coordinates 3 and 5. Alright, so this is what we call point discontinuity. So this is equal to 5. Okay, so this one, this is our L. Okay, so next we have asymptotic and or infinite discontinuity. So oftentimes we encounter asymptotic discontinuity when we get the undefined form. Okay, so take note, when we get the undefined form and we get an asymptote. All right, we get an asymptote. So note that asymptotic discontinuities are also considered infinite discontinuities. So asymptotic discontinuities are considered to be non-removable. Okay, so we cannot do anything about it. So this is considered non-removable since the discontinuity cannot be removed by filling a single point. Now, like for example, in this graph, we are given this function as x approaches to 3. Okay, so we cannot manipulate this function anymore, or this limit of the function anymore. So when you substitute x, value of x that is very close to 3, that is when x approaches 3, so the graph will approach, or will be getting closer and closer with this vertical asymptote. Okay, so this is an example of non-removable. Okay, any question? So when you speak of uh, essential discontinuity, so essential discontinuity is any discontinuity that is not removable. Okay, so non-removable. So this is an essential discontinuity. So that is a place where a graph is not connected and cannot be made connected simply by filling in a single point. So examples here are the step discontinuities and vertical asymptotes. Okay, so the step discontinuities and vertical asymptotes are two examples of this non-removable discontinuities or essential discontinuity. Okay, so an example here, as mentioned a while ago. So if you substitute x here equal to 3, so that makes the limit undefined. Okay, so we have this undefined form. So we get this asymptote. So the value of x that can makes the denominator equal to 0 would be the asymptote of the graph. Okay? So here we have what we call jump discontinuity. Okay, so oftentimes we encounter jump discontinuity when we have piecewise functions. Although this is not the only way to obtain jump discontinuity. Okay, so jump discontinuities are called to be non-removable since the discontinuity cannot be removed by filling in a single point. Now, like for example, this one, if you have the limit of the absolute value of x minus 3 divided by x minus 3 as x approaches to 3. So when you graph this function, you will see something like this. Alright? So it jump. Okay, so this is an example of jump discontinuity. Okay? So do you have any question? So essential discontinuity is when one or both of our one-sided limits does not exist or goes to infinity, it is called an essential discontinuity. So when one or both of our one-sided limits, so we have the left-hand side limit and the right-hand side limit, does not exist. So it can be just one of them or both of them does not exist or goes to infinity. So it is called an essential discontinuity. Okay? So this can occur when the radical expressions, or this can occur with radical expressions, inequalities, piecewise functions, etc. So essential discontinuities are always non-removable. So you have to take note that we can consider infinite discontinuities to be essential as well. Okay, so you see this example here. Square root of x, so limit of square root of x as x approaches to negative infinity. So when you graph this function square root of x, so you will see here this is half of the parabola. Okay. So by examining continuity, we can make four conclusions. Alright, so all polynomials are continuous, but all rational equations in the form of y equal to f of x over g of x, so these are discontinuous. So discontinuous when g of x is equal to 0. Okay, and all radical in the form of y equal to the a root of f of x are continuous, where a is odd root. Odd means 1, 3, 5, 7, 9, and so on and so forth. If that is the value of a here, this is odd, then this is continuous function. Then all radical in the form of y equal to a root of f of x are discontinuous, where a, the index here, which is a, is an even root. So discontinuous. And f, x, negative. Less than 0 means negative. Okay, so remember this concept, class. Odd root, continuous, even, discontinuous. Okay, so here we have some simple exercise based on the principles that we had already discussed and learned. So let's take this example. Find all points of discontinuity, state the type of discontinuity, and determine if it is removable or non-removable for the following. So we have example A. Okay, so our first example here, we're given a polynomial f of x equal to minus 3x squared minus 5x plus 1. So as we know, for a polynomial, as discussed earlier or in our previous session, so we can say that for all values of x, you will be able to find also get value of f of x. So in other words, the function is continuous. Alright? Then how about this one? We have a rational function here, f of x equal to x minus 2 divided by x squared minus 4. So for x equal to negative 2 and for x equal to 2. So what is this? What type of discontinuity that we have from this? And is it removable or non-removable or essential? So non-removable means essential discontinuity. Okay, so for this example, if you look at the numerator and denominator, and if you substitute these values here, so for example, for x equal to negative 2, using this value for x, if you're going to substitute it here, so minus 2, that becomes minus 4 at the numerator. Then minus 2 squared, that is positive 4. Positive 4 minus 4, that makes the denominator equal to 0. Right? How about if this is, so you have something divided by 0. How about if x equal to 2? So if x equal to 2, we have 2 minus 2, 0. So 2 squared 4 minus 4, so that is 0. So we have 0 divided by 0. Okay, so as mentioned or discussed in our previous session, if you have this 0 divided by 0, that indicates that both numerator and denominator has common factor. So it gives us an idea on what we can do from this part. Okay, so because we can expect a kind of discontinuity here, no, for x equal to 2, but this is removable discontinuity, because we can manipulate this. We can the denominator, we can write this as, so we can factor as x minus 2 and x plus 2. No, that is for the denominator. So x minus 2 times x plus 2. So these are the factors. Okay, so we have here the numerator, x minus 2. So we have x minus 2 at the numerator, and you have x minus 2 in the denominator. So x minus 2 divided by x minus 2 equal to 1. So this makes 1 over x plus 2. So now we can remove the discontinuity. Okay, so when x equal to 2, okay, so when x equal to 2, so what will happen? When x equal to 2, so 1 divided by 2 plus 2, so that becomes 1/4. Okay, so that's an example of removable. Now, at this point, at this value x equal to 2, so we can say that this is a point of discontinuity. So this is a removable discontinuity. Alright, so for x equal to minus 2, so we know that this is asymptotic. Okay, so asymptotic because we have something. Okay, we have something at the numerator, which is negative 4. The denominator is 0. So something divided by 0. So we have asymptotic. We have asymptote. So this is an example of asymptotic discontinuity. So non-removable. So this is an essential discontinuity. Okay. Now for letter C, we are given function equal to the cube root of x squared plus 2x minus 1. So the index here is 3. This is an add. So what is said a while ago. So this is a continuous function, because whatever values for x here, whether it's positive or negative, then since this is add, so you will always get the value for f of x. So this is a continuous function. So here we have f of x equal to the square root of x squared minus x minus 6. So this given, we can also manipulate this, or we can transform this, right? Because if you look at the radicand means the term inside the radical. So if you look at this, we can say that this is factorable. Okay, so what are the factors? So x and x, for this one we have negative here, we have 6. Factors of 6 is negative 6 is minus 3, positive 2, or plus positive 3, negative 2. Then since this is negative, so we choose our factors as, so x minus 3, uh, x plus 2. So how to check that one? You just multiply this one. Internal, okay? This, you multiply this minus 3 times x, so minus 3x, then multiply this external part. We have x times 2, 2x, so combine them, so minus 3x plus 2x, that is negative x, so the middle term come up. So therefore, this is a correct, these are the correct factors. Okay, so looking at this resulting or transformed expression, so we can say, because our purpose here is to get the value that is not negative, right? So we know how to do it, no? We had discussed last time on how to solve for the values. So you just, okay, if you have this number system, so we have x minus 3 times x plus 2 must be greater than or equal to 0, right? Otherwise, this is because the index here is even. So the requirement here, the radicand should always be positive or 0. Okay, so you have x minus 3 x minus 3 times x plus 2 this must be greater than or equal to 0. Okay, so after manipulating this, you will get this one, this interval, right? That our x must be greater than negative 2, but our x is less than 3. Okay, so those are the values that can give us a value for f of x. Otherwise, the values here becomes negative. So in that case, so we can say that this is an essential discontinuity. Okay, so non-removable. All right. So I hope you understood it, class, and you were able to follow what I was saying. Next, we have this continuity piecewise functions. So when dealing with piecewise function, we must consider where the function changes. Now, for example, we are given this piecewise function. So when you graph this one, you will see this kind of graph. So I'll not give you the details on how to graph this one. We have talked about this several times already. So I'm hoping that you know how to graph this one. Okay, so you consider this, if you consider this interval, if you have the number line system, if you have this number line system here, so we have 1 here. Okay, this is our 0. So when x is greater than or equal to 1, so in other words, you are considering this part here. Okay, this interval here. Okay, so all the values are in this part. So this is x greater than or equal to 1. Or you can say, sorry. So you can also write it this way. So we have here the bracket, we have 1, and the positive infinity. Okay, so that represent this interval. So all the values that belongs to this side here, including 1. But for, it means this is the blue one, right? This is for the blue one. But values, that is all values less than 1, all values less than 1. So it means this graph. So you use 1 minus x. Alright? So when you tabulate your values, so you consider this interval. So this interval here, so this is for our x less than 1. Or so if you use this kind of presentation, this would be your x can take the value of negative infinity from 1, excluding 1, to negative infinity. So this refers to this graph. Okay. So this is what we call jump discontinuity. So at x equal to 1, so you see here when you find the left hand limit, so you trace the graph down, no, as x approaches to 1. Okay. So this is the limit. All right. And if you continue moving, for example, you're asked to find the limit, no? The limit, for example, at x equal to 2. Okay, so while you're tracing the graph, so when you say from the left, no, from the left, so when you're tracing the graph, so this will jump down. You jump down and then continue going there. Okay, so this is an example of jump discontinuity, non-removable. So this is what is meant by it's not just space function that have this jump discontinuity. Also, this kind of function like this conditional function. It can also give us this kind of discontinuity. Okay, now the other one. So you have here our function is equal to 3 to the power x minus 1 for the interval x greater than or equal to minus 1. Okay, so this is our minus 1 here, right? This is our minus 1, this point. And your function would be 1 over x plus 1 for x less than 1. So the first condition, no, this condition here, x greater than or equal to 1. So it means that if this is our reference here, so all values, no, for this part. In other words, we are tracing this. We trace from the right going to this, meaning x approaches to negative 1. So we are tracing this one. Okay, tracing going in this direction. Okay, so this is the limit. Now considering this part, this is the limit. Then if you consider this interval, okay, so if you look at this x less than minus 1, so this is our 1. So we know that negative 1. We know that all the values on the left part of 1, negative 2, negative 3, negative 4, and so on and so forth, these are less than 1. Okay, so it means that when you trace the graph from the left towards negative 1, okay, so when you're tracing this graph, so you're approaching 1, negative 1. Alright, so it will continue and it will go indefinitely, and it will get closer and closer to this line. So this is the asymptote. Okay, this is the vertical, no, half of this one, because you cannot only this part here that this graph will get closer and closer to as x approaches to negative 1. Okay, so at x equal to 1, so at x equal to 1, so here, okay, I'll just remove this. So at x equal to 1, so this one here, so this is essential discontinuity. Essential discontinuity or infinite discontinuity. Why? Because as you trace the graph from the left, so it cannot go there, no? It can it just come here, then closer to, and it goes without bound. All right, so infinite, this is an infinite discontinuity. So there's no way that you can fill the gap by a single point. Okay, so at this x equal to 1. All right, so I think we have so much already about this continuity, discontinuity, this jump, non-removable discontinuity, essential discontinuity, and other kind of discontinuities. Now for the piecewise functions, so when dealing with piecewise functions, we must consider where the function changes. For example, you're given this kind of uh, function or expression. So for x greater than or equal to minus 2, so this is our minus 2 here. So for x greater than or equal to minus 2, so what are these values? So this belongs to this part here. Okay, so this part here means this part here. So this interval. Then for x less than minus 2, so x equal to minus x squared. So it means that all the parts, all the values of x in this interval here. In other words, we are just, for this part here, we are considering the blue graph. Okay? And if you consider this interval, so we are considering this red graph. Alright? So we can say that this is a continuous function. Okay? It's a continuous function. Now for D, x squared minus 4 divided by x squared minus 16. So x not equal to minus 4, right? Because when this is minus 4, so this will become 0. This becomes 0, 0 here, and 0 denominator. Alright, so when you graph this one, it will show you this kind of graph. So again, to graph, you just you can assume values for x and then solve for f of x. Of course, you have to consider the conditions here. That if x not equal to 4, so you use this. So not equal to 4, meaning you have 5, you have 3, right? On the negative as well, right? Because the condition is that x not equal to 4. So any values excluding x equal to 4, because this 4, x equal to 4, this makes the denominator equal to 0. So this can be considered as the vertical asymptote. Okay, so we say that at x equal to 4, so we can see that the graph is continuous. Oh, sorry, this one here. Okay, x equal to 4, the right hand limit. So you can see that this is continuous. And also if you look at this, I'm sorry, you see at x equal to 4, so here, this is the point. So continuous, the graph, this graph is continuous at this value for x equal to 4. You see, when you substitute it here, so 3 times 4, 12 minus 4, 8. So you have 1 over 8, very close to 0. Okay, so continuous. The function is continuous at this value for x equal to 4. X equal to 4, continuous. But for x equal to minus 4, x minus 4, so this is our x minus 4 here. This is our x minus 4. So at this value for x, so you see, this makes this is minus 4, so minus 4 squared, 16, 16 minus 16, 0. So this makes the denominator 0. But the numerator is not 0 because negative 4 minus 4, so it is minus 8. But here at the denominator, this makes denominator equal to 0. So this is the vertical asymptote. x equal to minus 4 is a vertical asymptote. So we know that for asymptotic discontinuity, this is non-removable. Okay, so I hope it's clear, and I think that's all. Thank you very much, and I hope that you really was able to follow me. Now, if you have studied the previous two parts of the videos on this topic, I'm sure that you were able to follow all what I said, all what I describe and show to you the calculations. All right, so thank you once again, and have a nice day, everyone. Stay safe and healthy always. God bless, and bye for now.